If you got to this video by clicking on the spreadsheet right here, then you already have both things that you need. But if you got to the video from YouTube, then you need to get to the spreadsheet, and you can do that by going under the video to the description, and there's a link to the spreadsheet there. You do need both the spreadsheet and the video to be able to do this lab activity, because in the video I'm going to rotate this around and shine the laser at various angles of incidence, and then you're going to measure the angle of refraction. So for every 5 degrees angle of incidence, from 5 to 60 degrees, you'll pause the video and toggle back and forth and measure the corresponding angle of refraction. And this spreadsheet, just like all my other spreadsheets that I've created, these cells will turn green when you type in the right number or the right formula. So you get feedback on whether you're on the right track or not. So here's the situation. I have this clear prism, and I don't know the index of refraction for it. I don't know how fast light travels through it. We're going to calculate that too. But we're going to not just use a single data point to find those two things. We're going to use a graph. So we're also going to be practicing linearizing data. And we're going to use Snell's law to do that. The index of refraction in one medium times the sine of the angle in that one medium equals the index of refraction in another medium times the sine of the angle in that other medium. And we can calculate the index of refraction by taking the speed of light in a vacuum divided by the speed of light in that medium. So we have a ray coming in like this, and we have to measure the angle of incidence, but we do so off of the normal. We're going to call this the angle of incidence. In this case, it was about 40 degrees. And the angle that this makes, we read off of the protractor here, and it looks like it's right at 25 degrees. We'll call that the angle of refraction. Anytime light or a wave goes from one medium to another, some of it's going to refract into the new medium, some of it is going to bounce off and reflect, and we would call that the angle of reflection. The law of reflection states that the angle of incidence would equal the angle of reflection. So we're going to, in just a moment, rotate this around, and you're going to pause every 5 degrees, right on as close as you can, and measure the corresponding angles of refraction. So before you do that, just make sure that your settings in YouTube, click the gear there and choose the highest resolution that's available. So here we go. Okay, so you paused and stopped at every 5 degrees. Right now, that first column, or the second column, the angle of refraction, you have completely filled out. If you know how to proceed, go ahead and run through the spreadsheet. If you need a little more help, stick around. I will help a little bit, but there is a second part to the spreadsheet. There's another tab at the very bottom called the critical angle, and we're going to do that too. So here's a little help on that first part. We have Snell's law, and our first medium is the prism, our second medium is in air, and we would like to use all those data points to find the index of refraction in the prism. To do that, we have to manipulate the equation a little bit so that we can linearize the data in a graph, including all the data points. So we recognize that as the equation of a line, the slope and the intercept, the x-axis and the y-axis. So instead of graphing the angle that it made in the air and the angle it made in the prism, that wouldn't give us a straight line. We graph the sine of the angle in air on the x-axis and the sine of the angle that it made in the prism on the y-axis. I guess I should have said that this term here I divided and got down over here. But this is a constant and that is a constant. So when we have a constant in front of the thing we're graphing on the x-axis, that constant is going to equal the slope of our graph. And we can use the slope function in the spreadsheet to calculate the slope of all those data points. Since the index of refraction in air is 1 to within 3 sig figs, we know the slope from the spreadsheet, we can rearrange that, take this term, move it over here, this term, move it down over here, and we can find the index of refraction of our prism by just taking 1 divided by the number we got for slope. We also would like to calculate how fast light travels in our prism. So the index of refraction of our prism, speed of light in a vacuum, and the speed of light in our prism. We can switch those two variables by multiplying both sides by that, dividing both sides by that, and I can find the speed of light in our prism by taking the speed of light in a vacuum divided by the index of refraction in our prism. The second part to the lab, you have just completed this part, the index of refraction, filling out the spreadsheet. But now there is this tab here that takes you to a different spreadsheet, and we're going to do this for a triangular prism now. What the question is at what angle do we have to be incident upon this surface so that it produces the critical angle on this surface? Now the critical angle is the angle that we have to be incident upon this surface to make it refract at 90 degrees on this surface. Now, in this example, it was 30 degrees, but it didn't quite refract at 90 degrees. It came out a little less than 90 degrees. One thing we also have to be careful of, and maybe you even realized it on the first part, is that spreadsheets are permanently in radian mode. Any angle you give to sine, cosine, or tangent, it assumes that angle was in radians, not degrees. So we do have to convert into radians first. And there is a function that gives you the syntax right there. So we have this ray of light coming in, and it's going to refract like that. And then again, our question is, what angle do we have to approach at so that it refracts at 90 degrees? So what angle here is going to produce 90 degrees over there? We'll call this angle D, and this is going to be our critical angle, and we want this to be 90 degrees. So to find this, we're going to work backwards. We're going to use Snell's law, knowing that this was 90 degrees. What would this be? And then knowing this, we can find angle D here and use Snell's law to find out what this is. A little hint here, there is a triangle in here. It's an equilateral triangle, so it's also equiangular. This angle is going to be 60 degrees. So knowing that, I could find this angle. This is 60 degrees. And then knowing that whole triangle, I could find out what this is. And knowing what this is, I can find D, and then use Snell's law to find that. Okay? So you're going to use a spreadsheet to find a really precise measurement for this angle. But let's play the video here and see measuring it directly and see if Snell's law really does work for us. So I'm going to play the video. You're going to hit pause and see when this line here gets parallel to that edge, or when it refracts at 90 degrees, you're going to see what angle of incidence it is. So let's do that. So right about there. If you need to toggle back, you can, but see what answer you got there, and then do the same thing in the spreadsheet and see how those two answers compare. But that's Snell's law, angle of incidence, angle of refraction, and how those relate to the critical angle.